Hi guys, how are you all? Okay, welcome back. So today we are going to start to revise geometrical optics. Hi guys, how are you all? And we will discuss some questions from the sample papers, this year's sample paper 2021, and few questions from last year. So we will try to cover as much as possible in our 1 hour session. Okay. So let's start. And what we are going to cover in this chapter that I'll discuss with you guys. So the topics which we are going to discuss, in fact, a question based on these topics. So what we have questions. So I'll discuss a little bit detail of the concept, the background concept, and then we will discuss the question also. So we have questions based on total internal reflection, right? We have questions based on convex lens image formation. We have question based on combination of lenses. We have question based on astronomical telescope, and we have questions based on prism. Fine. So we have questions from last year and sample paper. Good evening. Good evening. So we have questions from last year and sample papers. So we will focus on that and we will try to do as much as possible. Okay, guys? तो चलो फिर start करते हैं. So this question is from this year's sample paper 2021. Okay. अब आपको यहाँ दिख रहा है, it's a diamond. The heading is sparkling brilliance of diamond. Okay. तो अब ये क्वेश्चन किस हिसाब से है, क्या है, इसके लिए आप देखें, ये पैसेज बेस्ड क्वेश्चन अब आपको सीबीएसई मिलेंगे इस साल से, कि कंटेंट होगा, फिर उस पैसेज पे बेस्ड 4 या 3 या 5 ऑब्जेक्टिव क्वेश्चंस होंगे. तो यहाँ पे ये आपको डायग्राम दिखाया गया है. इट्स एन इमेज एंड रिलेटेड टू दिस इमेज सम इंफॉर्मेशन इज गिवन हियर, लाइक the total internal reflection of the light is used in polishing diamonds to create a sparkling brilliance. By polishing the diamond with the specific cuts, it is adjusted. Most of the light rays approaching the surface are incident with angle of incidence more than critical angle. तो इस पैसेज में ही आपको बहुत कुछ बता दिया गया है that what is total internal reflection, what is happening here. So most of the things are already mentioned. तो पैसेज बेस्ड क्वेश्चन आपका बहुत इजी होने वाला है. आपको पैसेज अच्छे से रीड करना है. ओके, यू हैव टू रीड पैसेज वेरी इफेक्टिवली. अब इस पैसेज में यही स्टोरी आपको बताई गई है कि हाउ अ लाइट इज एंटरिंग इनटू अ डायमंड. यहां देखो, यहां इंसिडेंट हुई लाइट एंड देन लाइट एंटर्स इनटू द डायमंड. बट एट दिस पॉइंट यू कैन सी लाइट इज टोटल इंटरनल, इट इज अंडरगोइंग टोटल इंटरनल रिफ्लेक्शन, है ना. So most of you know what is total internal reflection, right? यहां हिट करना और इसी मीडियम में वापस चला जाना, दिस इज टोटल इंटरनल रिफ्लेक्शन. तो इसका मतलब ये है कि यहां अगर आप नॉर्मल ड्रॉ करोगे तो ये जो एंगल ऑफ इंसिडेंस है ना, ये एंगल ऑफ इंसिडेंस, ये क्रिटिकल एंगल से ज्यादा होगा. आपको याद है ना बच्चे, टोटल इंटरनल रिफ्लेक्शन क्या होता था? अगर ये डेंसर मीडियम है, ठीक है, अब थोड़ा सा इसका कंसेप्ट डिस्कस कर लेते हैं, फिर आप क्वेश्चन करेंगे. डेंसर मीडियम है, ये आपका रेरर मीडियम है. अगर लाइट डेंसर से रेरर में जा रही है और ये एंगल एक ऐसा एंगल है जिसपे रिफ्रैक्टेड रे बिल्कुल पैरेलल हो जा रही है सरफेस के, इसका मतलब ये एंगल क्या है बच्चे? ये एंगल ऑफ रिफ्रैक्शन है विच इज 90 डिग्री. तो इस एंगल को कहते हैं हम क्रिटिकल एंगल. तो अगर एंगल ऑफ इंसिडेंस आपने क्रिटिकल एंगल से ज्यादा कर दिया, फिर क्या हो जाएगा? टोटल इंटरनल रिफ्लेक्शन. मतलब इस एंगल को अगर आपने बढ़ा दिया, आपने एंगल ऑफ इंसिडेंस फॉर एग्जांपल इतना ले लिया बच्चे, ये देखें, आपने थोड़ा ज्यादा ले लिया एंगल ऑफ इंसिडेंस क्रिटिकल एंगल से जरा सा ज्यादा, फिर क्या होगा? ये रे वापस सेम मीडियम में आ जाएगी. कोई भी पोर्शन इसका बाहर नहीं जाएगा रेरर मीडियम. इसे बोलते हैं टोटल इंटरनल रिफ्लेक्शन. अब मैं आपसे पूछता हूं कि अगर मैं आपसे पूछूं कि क्या क्रिटिकल एंगल निकाला जा सकता है, आप बोलोगे सर बिल्कुल, या वी कैन एब्सोल्युटली फाइंड क्रिटिकल एंगल. एंड हाउ वी कैन फाइंड दिस क्रिटिकल एंगल? सो फॉर दैट लेट्स सपोज कि this medium has refractive index n1 and this medium has refractive index n2. So to find the critical angle, what we can do, bacha, we can apply Snell's law at the point of incidence. यहाँ. So when we apply the Snell's law क्या बोलता है? Sin I. What is I here? Theta C, right? Yeah, sin I. I is theta C divided by sin R. What is R? 90 degree. At critical angle, angle of refraction in rarer medium is 90 degree. So we will take sin R, matlab 90 degree, is equal to N2 by N1. N2 by N1. Sin 91 होता है, तो यहां से from here you get critical angle formula sin theta C is equal to N2 by N1. N2 is less refractive index, N1 is more. Yeah? Chalo. Now we will see what is the question being asked here on the basis of this concept of total internal reflection. अच्छा, एक total internal reflection यहां हुआ, फिर लाइट यहां हिट की और यहां भी इसका TIR हुआ, राइट? बाहर नहीं गई अभी लाइट, और फिर लाइट यहां हिट करेगी, यहां भी इसका TIR हो गया, राइट? इस तरीके से एक लाइट जब डायमंड के अंदर एंटर करती है ना, इसका मल्टीपल टोटल इंटरनल रिफ्लेक्शन होता है। और टोटल इंटरनल रिफ्लेक्शन बहुत आसानी से हो जाएगा अगर क्रिटिकल एंगल बहुत कम है तो, ठीक है? मतलब आपको ये एंगल ऑफ इंसिडेंस ज्यादा रखने की जरूरत नहीं है, बहुत कम भी होगा तो आपका TIR हो जाएगा, क्योंकि क्रिटिकल एंगल बहुत कम है। ओके गाइस, अब आते हैं इस पे क्वेश्चन देखते हैं कि सीबीएसई ने क्या क्या क्वेश्चन पूछा है। पहला क्वेश्चन क्या पूछ रहा है ये देखें, लाइट कैन नॉट इजिली एस्केप अ डायमंड विदाउट मल्टीपल इंटरनल रिफ्लेक्शन। दिस इज बिकॉज ऐसा क्यों होता है, व्हाई इट इज हैपनिंग that light cannot come out without having multiple internal reflection? Because for diamond, guys, look carefully, diamond has maximum refractive index around 2.42. तो अगर हमारा rarer medium air है, बात समझना, listen to me carefully, if our rarer medium is air and denser medium has some refractive index, then this formula will be modified like this: sin theta से क्रिटिकल एंगल इज इक्वल टू N2 क्या हो जाएगा बच्चा, एयर, तो रिफ्रैक्टिव इंडेक्स 1 होता है, और मीडियम का रिफ्रैक्टिव इंडेक्स जो कि यहां डायमंड है, आप उसे N ले लो। नाउ दिस N इज द रिफ्रैक्टिव इंडेक्स ऑफ एनी मीडियम, हियर दिस N इज द रिफ्रैक्टिव इंडेक्स ऑफ डायमंड। तो रिफ्रैक्टिव इंडेक्स मीडियम का जितना ज्यादा होगा, यू नो, N, critical angle will be minimum. So because diamond has maximum refractive index, so it has minimum critical angle. So we can say it is very easy for a light to undergo TIR in diamond. Why? The requirement of critical angle is very less. That's the reason जैसे ही light diamond में enter करती है, it goes multiple total internal reflection. Why? You can say reason is very high refractive index or very less critical angle. तो let's move to the question. अब देखें यहां पर, this is because multiple internal reflection क्यों होता है? This is because its critical angle with reference to air is too large. No, refractive index is high, so critical angle is less. So this is not possible. Let's read the second one. Its critical angle with reference to air is too small. Yeah, critical angle is very small. So all the angle of incidence is technically more than critical angle. So what happens? Light goes multiple TIR. So this one is correct. This one is not correct. Diamond is transparent. Being transparent has nothing to do with TIR, right? Rays always enter at an angle greater than critical angle. Is it true? No, it's not true, right? Rays can enter into the diamond with incidence angle less than critical angle also, okay, or more than it can enter at any angle of incidence. So this is also not possible. Okay, now let's move to the second question, guys. The critical angle of diamond The critical angle of diamond is 24.4 degree. Please understand, 24.4 degree. Very, very small critical angle, right? Then its refractive index is very easy to find. What we will do, we will write sine theta c is equal to 1 by n, right? So from here, sine theta c, that this is what given. Theta c is given 24.4 degree. So sine 24.4 degree is equal to 1 by n. So from here you can find refractive index easily. N is equal to 1 by sine 24.4 degree. Now you take calculator, find the value of sine 24.4 degree, and then when you will solve it, 1 by sine 24.4 degree, you will get it 2.42. So this is the correct answer. I know it is not possible to calculate sine 24.4. So what I can guide you, 24.4, you can treat it approximately 30 degree, right? And sine 30 is how much, guys? Sine 30 is 1 by 2. So 2 will go up. So that means the refractive index will be close to 2. And the only option where refractive index is close to 2 is 2.42. Yeah, it should be more than 2 actually, because sine is less than 30 degree, right? So it should be more than 2. So the only option is A. Okay, guys, next question. Let's move to the next question. The basic reason for the extraordinary sparkle of suitably cut diamond. See, if you cut the diamond like a glass slab, do you think that light will remain in the glass slab made of diamond for a longer time? Not possible. See, the value of diamond is because of its refractive index and because of its cutting process. You see, you have to cut in such a way that if light gets totally internally reflected from here, then it hits another surface. So possibility is that at another surface, the angle of incidence should be greater than the critical angle. So cutting is a technical thing, right? So cutting is important point. Otherwise, if you have diamond in shape of glass slab, then it won't work for you, right? You won't get the same result. So the correct answer should be what here? Extraordinary sparkle of suitably cut diamond is that it has low refractive index. No, diamond has high refractive index. No, it has high transparency. As I already told you, transparency has nothing to do with TIR, right? It has high refractive index. Yes, this is the correct answer. It is very hard, doesn't make any sense. Yeah. So high refractive index, less requirement of critical angle. So when you will cut the diamond, you will make sure that all the angle of incidence at any part of the diamond should be more than the critical angle. This is how you cut the diamond. Okay. Next. Okay, read this question, guys. A diamond is immersed in a liquid with refractive index greater than water. This is really important point, guys. A diamond is immersed in a liquid with refractive index greater than water. Then the critical angle for total internal reflection will be, I need your attention here. What was the critical angle formula? Sine theta c is equal to n2 by n1. And n2 is the refractive index of rarer medium, and n1 is the refractive index of denser medium. So in the first case, you have rarer medium as water. That means you kept diamond in the first case in water, right? In second case, you keep the same diamond in a liquid with a refractive index more than water. So tell me, N1 is for diamond, which is same in both cases. I hope you guys are getting it. N1 is same in both cases, which is diamond, right? But here, it's a different liquid which has refractive index more than water. So if I ask you the ratio N2 by N1 is more in first case or in second case, this N2 of liquid is more than water. So that means N2 by N1 is more in the second case, right? So you can say sine theta C is more in second case when the diamond is kept in a liquid. So in that case, because N2 by N1 is greater, so theta C in the second case will be greater than theta C in the first case. First case, you keep the diamond in water. Second case, you keep the diamond in the liquid. So what will happen? Because the ratio increases, so the critical angle will increase in the second case. So the question is asked, then the critical angle for total internal reflection will be decrease? No. Remain same? No. It increases, right? Will depend on the nature of the liquid. Obviously, it depends on the nature of the liquid, but the nature has been mentioned in the question that it has a refractive index greater than water. So I hope you guys understand it. Okay, guys, let's move to the next question. If you have any question, please comment in the chat box. In the comment, I'll just check it. Okay, guys, I want an answer from you. Let's read question number 5. The following diagram shows the diamond cut into different shapes. So you will see how the cutting affects the total internal reflection, right? In two different shapes. One shape is this and another shape is this. Here you can see light enters like this perpendicularly. So you know it will go without deviation here. Then it hits here. And now you can see TIR is taking place here, total internal reflection. Why? Because this angle is more than critical angle. Yes, that's why TIR is taking place here. Yeah. And what about here, guys? Again, if this angle is more than critical angle, so obviously this should also be more than critical angle. So TIR again here. And then it becomes parallel to this. So it is hitting this surface perpendicularly. So no TIR, it will go straight. Correct? So how many TIR you have seen here? 2 TIR in this diagram. Here, look at the shape of the diamond. It is cut like this. So it enters perpendicularly, so it goes without deviation, right? But now you can see that this angle is very small angle. So this angle is less than critical angle. That's the reason TIR is not taking place here. Yes, and it is going out away from the normal because it is coming from denser to rarer. So it goes away from the normal, right? Now here no TIR, here 2 TIR. So light will be trapped for a longer time in this diamond, not in this diamond. Yeah. So if we talk about the sparkling quality, the brilliance of diamond in the second diamond will be less. Why? Because the light is not trapped, no multiple internal reflection here. But here you have 2 multiple internal reflections. Yeah, 2 internal reflections. So we can say the brilliance of diamond in the second diamond will be less than the first. Why? Okay, in second, you can see the shape is like that the critical angle, you know, few lights maybe undergoing TIR, few rays, but majority of rays are going TIR here, right? So this is the reason light is trapped for a longer time in the first diamond. That's why the brilliance, the sparkling quality, the brightness will be more in the first case and less in the second case. Okay, guys, I hope you understand it. Good. Let's move to the next part. Now, this is the question which is really very, very important question. And this question is related to, again, Snell's law and prism. So read the question. A triangular prism of refractive index 60 degree, refracting angle 60 degree. So this one is refracting angle, yeah, we call it A. So A is given here 60 degree, is made of transparent material of refractive index 2 by √3. That means N, the refractive index here of the prism is given 2 by root 3. A ray of light is incident normally on the face. You can see guys here, it incident normally on this face, KL, as shown in the figure. Trace the path of the ray as it passes through the prism. That means now we have to trace the subsequent path. After entering into the prism, what path the ray will take, that's what we have to trace, we have to draw. And then there is a question, calculate the angle of emergence and the angle of deviation. So I want to know from you what is angle of emergence and what is angle of deviation. Okay, just think about it, comment it, and now we will start solving it. So guys, tell me, if it hits perpendicularly, will there be any bending? No. So it will go straight like this. It will go straight like this. Straight like this. Now here we need to draw a perpendicular. I hope you understand it. We need to draw a perpendicular here. So we are going to draw a perpendicular. Fine. Now, if this angle is less than critical angle, what will happen, guys? It will go out. If this angle is exactly equal to critical angle, what will happen? If this angle is exactly equal to critical angle, what will happen? The path of light will become parallel to the surface, right? It won't go out, neither will come back inside. Now, if this angle is more than critical angle, what will happen? TIR will take place. So first of all, let's talk about how much is this angle. So it's very easy to identify because we know this is 90 degree. 90 plus 60, 150, right? 90 plus 60, 150. So this should be 30 degree, right? So that total is 180. And if this is 30, this should be 60 degree. I hope you guys understand it. Look, 60, 90, 90 plus 60, 150. And this should be 30. And because this is perpendicular, so this should be 60. So that 60 plus 30 is equal to 90 degree. Now, we need to understand whether this 60 degree is less than critical angle, more than critical angle, or equal to critical angle. Then only we will be able to draw the subsequent rays. Yeah. So let's find out critical angle, guys. What is the formula for critical angle? You know, the rarer medium is air. So we will simply write sine theta c is equal to 1 by n. Now, so we have n as 2 by root 3. So 2 by root 3. So root 3 goes up, root 3 by 2. Sine theta c root 3 by 2. What does it mean, guys? It means critical angle is 60 degree. Critical angle is 60 degree. And here, angle of incidence is also 60 degree. So what is going to happen here? When the angle of incidence is exactly equal to critical angle, it overlaps with the surface. So this would be the situation with the ray. And we can say that here angle of refraction in the rarer medium is 90 degree. I hope you guys are getting it. Yeah. So this is angle of refraction, which is equal to 90 degree. Yeah. Yes. So this is what first part is done. Trace the path, that is done. Next part is calculate the angle of emergence. Okay. And angle of deviation. So I want to know from you, what is angle of emergence? What do you see? What is the angle of emergence here? Right? This angle is angle of emergence, right? Which is 90 degree. That means it emerges parallel to the surface. So I think this is also done. So angle of emergence, what you say is E is 90 degree. So it overlaps with the surface. Next is angle of deviation. So do you remember the angle of deviation formula? It was I plus E minus A, angle of prism, refracting angle of prism, right? So I is how much, guys? If you look carefully, I is 90 degree or 0 degree. Tell me here. I want to know from you. eye here, is it 90 degree or 0 degree? Angle of incidence is 0 degree. Yeah, yes, because you have to draw the normal, so the normal will be parallel here. So I is 0 plus E, angle of emergence is 90 degree, minus angle of prism is 60 degree. So 90 minus 60 is 30 degree. So 30 degree is the deviation. 30 degree is the deviation, which is quite logical. Yeah, because you see, if I show you the deviation, this is the deviation, guys. The ray has to go straight like this, and this much is the deviation, which is, this is 60, so this is 60, so deviation is 90 minus 60. Quite clear? So this is 30 degree. Okay, so it was really a good question. You can expect the same type of question in your coming board examination. So please mark this question, practice 2-3 different, different questions of the same type. है ना? So CBSE में there are chances that this question will be asked and in 3 marks, not in 2 marks. 3 marks में आ सकता है आपको. चलो, let's move to the next question. A double convex lens is made of a glass of refractive index 1.55 with both faces of the same radius of curvature. Find the radius of curvature required if the focal length is 20 centimeter. Now, when you read the question, try to recall what is the concept behind. The concept is that you have a double convex lens. So you should know what is double convex lens. That means both sides of the lens is convex. So this is double convex lens, right? And if the radius of curvature of this side and this side is same, then we call it equiconvex lens. So here it is said, will both faces of the same radius of curvature. So we may call it equiconvex lens. So this radius of curvature, which we generally say R1, we can treat it as R, and this radius of curvature as R2, and we have to take it R only because it is mentioned in the question. Refractive index of the lens is given 1.55. Fine. The question is asked, find the radius of curvature so that the focal length of the lens is 20 centimeter. So this question is based on lens maker's formula. So guys, who remember lens maker's formula? Tell me. This question is based on lens maker's formula. The formula is 1 by f, focal length of the lens, is equal to n2, refractive index of the lens, divided by n1, refractive index of the surrounding of the lens in which the lens is kept, minus 1, and then 1 by r1, radius of curvature of the first curvature, the left side, minus 1 by r2, radius of curvature of the right side of the lens. Now this is lens maker formula, guys, and this formula is valid for all types of lens: equiconvex lens, plano-convex lens, concavo-convex lens, concavo-concave lens, plano-convex lens, plano-concave lens. कोई भी तरीके का lens हो, this formula is valid. So this question is basically based on this formula only, right? Now let's see how we solve this question. Okay, so coming here, it says the focal length would be 20 centimeter. 20 centimeter. So in place of focal length, we will keep 20 centimeter. Please understand, I'm not converting centimeter into meter. Okay, and because I'm not converting centimeter into meter, so the radius of curvature I'll get in centimeter only. Okay, so you don't need to convert it. Now guys, tell me, what is n2, the refractive index of lens? It is 1.55. What is the refractive index of the surrounding medium? You see, nothing is mentioned about surrounding medium, right? What is the surrounding medium of the lens? So in this particular case, conventionally, we treat the surrounding medium as air. So if it is air, N1 is 1, minus 1, 1 by R1. Now you need to see how you are going to take R1. Are you going to take R1 as positive or negative? Yeah, you have to decide it yourself. So if you suppose that the light ray is coming this way, if you suppose this is the direction of incident ray, then according to sign convention, R1, this curvature has center this side, right? And optical center is here. So to measure the distance R1, you will move right side. That means in the direction of incident ray, yeah? So you will take it positive. So R1 will be taken positive. R1 is plus R, okay? And look at this curvature. Its center opens on the left side. So from optical center, you will move in this direction, opposite to incident ray. So according to sign convention, you will take this distance as negative. So minus R. So here it should be R2 as minus R, fine. Now you can write it further like this, 1 by 20 is equal to 1.55 minus 1 is actually 0.55. 1 by R and minus minus becomes plus. 1 by R plus 1 by R is actually 2 by R. So from here you get radius of curvature is equal to 2 into 20 is 40. So it is like 40 into 0.55. So when you multiply it, see what you get. I can calculate it. Let me calculate it. So 40 into 0.55, it comes 22. It comes 22. So 22 centimeter. Why centimeter? Because I haven't converted centimeter into meter. I have taken focal length as 20 centimeter only. So the radius is in centimeter only. Okay. Okay, so I hope guys you understand this. So let's move ahead. Let's move ahead. So this was a good question again. Just practice the same type of questions because for sure you are going to get a question like this. So let's move on further. Now, draw a ray diagram depicting the formation of the image by astronomical telescope in normal adjustment. So now you have to recall, we will deal with the first part, part A first, okay? So you have to recall what is astronomical telescope, how do we design it, right? So astronomical telescope, we use to see the object far away from us, like stars, planets, yeah, galaxies. So for this purpose, we use two convex lenses, one of large focal length and one of short focal length. We call objective and eyepiece, right? So this is one lens. I would always suggest you to draw like this. So first you draw objective. Don't draw eyepiece first, okay? Objective. So it has high focal length and high radius of curvature. So this radius of curvature and this radius of curvature should be high, focal length should also be high. So focal length of objective as FO, and we can take both radius of curvature as same RO, RO, O for objective. Why we call it objective? Because if we are looking at a star, let's say we are looking at a star, and the star we know it's far, far away. So technically speaking, the rays will come from infinity. Object is at infinity. So the two rays will come parallel, right? So let me draw the principal axis. Now, what I told you, for example, if we are looking at a star or planet, so objects are far, far away. Technically speaking, they are at infinity. So the rays will come parallel. Fine. So we will take two parallel rays and we will take like this. One ray, take it like this. Another ray we can take like this. And we know it will, these two rays are parallel, so they will converge at focal plane, in focal plane. So if I converge this ray, so you can see they converge here. So this is the focus of, you can say this is the focus of this objective lens, right? Now the both ray will hit the eyepiece. So we need to draw eyepiece now. So that's why I told you, just wait and then you will draw eyepiece like this. Okay? Now it's very easy for you to draw the eyepiece and you will draw it like this. Like this. This is eyepiece. Why we call it eyepiece? There is a reason for that and we will just mention it why. Now, it is said that the astronomical telescope is in normal adjustment. So guys, what happens in normal adjustment? You see the final image is at infinity and your eyes are relaxed. Yeah. So the final image is formed by eyepiece. And if the final image is at infinity, then from here, the ray should go parallel like this. And your eye is somewhere here. Right? So that's why this lens is called eyepiece, because it is close to eye. Eye is this side. Now, if you extend it, the image is formed at infinity, right? At infinity. Intermediate image property you can see is inverted and real. Intermediate image. Final image is at infinity. Yes? Yeah. So eyepiece is again has short focal length as compared to objective, you can see. So we call eyepiece focal length as FE, and the radius of curvature you can suppose RE. Now, if radius of curvature is more, focal length will be more. Correct? So this is the representation, and for this representation, you will get 1.5 marks easily. Okay? So this was the first part. Draw ray diagram depicting the formation of the image by an astronomical telescope in normal adjustment. Done, guys? So don't draw the eyepiece, otherwise most of the time what happens, the ray goes down and the eyepiece is above. So to avoid that confusion, that mistake, you draw objective first and then take the rays, the two rays, and then you draw the eyepiece accordingly. Okay, perfect. Good. Now let's move to the part B, guys. Okay. You are given the following three lenses. Which two lenses will you use as an eyepiece and as an objective to construct an astronomical telescope? So basically, look at this. You're given three lenses. Which lens you will choose as an objective and which lens you will choose as an eyepiece? So before you choose it, I'll just tell you what is the purpose of this objective lens and eyepiece lens. You see, guys, there is something called resolution. There is something called resolution. If you use a good telescope and you try to resolve the images, there are many options in your telescope. So if you try to resolve the images, you will be able to see these spots on the surface of the Mars, or you take your iPhone, your phone, your mobile phone, and just try to enlarge the image, resolve the image, then you would be able to see the threads, individual threads of your cloth. This is called resolution. See, magnification is different thing. Magnification means an enlargement of the object, that's it. But if there is no clarity, there is no resolution. If you are able to see each and every thread of your t-shirt, then this lens has a better resolution. And we know that resolution, first you see a star is there. Star looks like a dot to us, right? If we look with naked eyes, a star appears to us as a dot. But when you look with telescope, you find it's not a dot. That means you resolve the image of a star, and that resolution is done by objective. Fine, please understand. So this image which is formed here now, this is resolved image. Resolved image, it is clear image. You can see the clarity in stars, and that resolution is done by objective. And resolution we see is more if the radius of curvature is more. Obviously, if radius of curvature is more, the focal length of objective is more. That's the reason objective in astronomical telescope is of large focal length, or you may say large radius of curvatures, because if radius of curvature is more, focal length is more. And this resolved image is magnified by eyepiece. You just, eyepiece is just resolving it further a little bit, but it is primarily enlarging this image, So the best resolution done by objective, and then eyepiece resolve a little bit only, but primarily it magnifies that resolved image. Okay, so you understand the purpose. So for this reason, so objective focal length is larger than eyepiece focal length. Yeah, and similarly, radius of curvature of objective is more than radius of curvature of eyepiece. So we have given 3 possible situations. We have to choose which one is correct. So let's come here. L1, L2 and L3. L1, power of L1 is given 3 diopter. Achha, please understand that the power of a lens is inversely proportional to focal length. So focal length is inversely proportional to power. Less power means more focal length. So I think out of the 3, the minimum power is this. So that means here radius of curvature is, focal length is more, so radius of curvature is more. So we are going to use as radius of curvature of objective of focal length of objective, this lens. I hope it is clear. Yeah. Yes. Now aperture is 8 centimeter also. So now you, from here you can understand focal length is more and aperture is also more. So the L1 we should use as objective. Quite clear, right? Now look at L3. Power is more, so focal length will be less. Yeah, power is more, focal length will be less. So less focal length, so we can use it as eyepiece. And aperture is same in both cases. So obviously this will be taken because it has less focal length. Okay, guys. So this would be used as eyepiece. So L3 will be used as eyepiece. So I hope it makes sense, guys. Is this clear? Fine, guys. So L1 is objective, will be used as objective, and L3 will be used as eyepiece. So please understand, in an astronomical telescope, we use L1 objective. I mean, the objective lens should be of large radius of curvature and large focal length. Eyepiece should be less, should have less focal length and less radius of curvature, right? And why eyepiece should have less focal length? So there is a reason for this. If you remember angular magnification, in case of normal adjustment, it was D by FE, right? Angular magnification is done by eyepiece. angular magnification is done by eyepiece. So less focal length means more angular magnification. Better is the lens. That's the reason eyepiece focal length should be less, right? So this is the reason, guys. I hope you guys understand it. Now there is last question. Let's do this quickly and then we will finish it. This one is the last question. Draw a ray diagram to show the formation by a combination of two thin convex lenses in contact. Ray diagram we have to draw. Obtain the expression for the power of the combination in terms of focal length of the lenses. Okay, so the question says two convex lenses are in contact. Fine. So draw the two convex lenses. Like I would say, take this one of focal length f1 and this one as focal length f2. Both are convex. It is given in the question. So what we have to draw? Ray diagram first of all. So we can take object anywhere. For example, suppose object is here. So I can take one ray like this. Now what will happen? This is convex lens, so it will converge it. So let's say it converges like this. Right? So it has to, I mean, if this second lens was not there, then this ray would have come to this position. We call this intermediate image, I prime. Yeah, and I can take this distance as V prime, intermediate image distance, and this distance as U, object distance. But we know that here also a refraction from the second lens will take place. Second lens is also converging, guys. So it will again converge this ray even further. So this ray gets converged here. So this is the final image, guys. This is the final image I, and we call this distance as the final image distance V. Okay. Now, obtain the expression for the power of this combination. So when we talk about combination, you can see the combination behaves as a converging lens only because both rays are converged only, right? Both lenses are converging only. So if I draw an equivalent lens, it should be converging only, right? So because the lenses overall rays are converged, so I draw an equivalent lens and I don't know its focal length. I suppose it's f, fine. And I'll keep the object at the same distance as you see in the combination here at the same distance. So this would be object distance. And the ray goes like this and it will converge. So let's say finally it converge here. This is the final image which you have here, I. And this distance is V, the final image distance. So these two situations are equivalent situation, identical situations. So I have to obtain the expression for the power of the combination. So if I am able to find the focal length of combination, the power of this can be written as 1 by f. I hope you guys understand it. So what I would do, I would write lens formula here individually for the first lens. So what is the lens formula, guys? 1 by V minus 1 by U is equal to 1 by f. So it is 1 by, for the first lens, 1 by V prime. It should be taken positive because on right side, minus 1 by U is equal to 1 by f1. Okay, guys, tell me, U should be taken positive or negative? U. It should be taken negative, right? So when you take it, let's write it negative. So it would become 1 by V prime minus plus 1 by U is equal to 1 by f1. This is equation first. For the second lens, guys, I can write final image is V, image distance. So 1 by V minus 1 by U. U is actually V prime because this intermediate image acts as an object for the second lens. So I should write it 1 by V prime positive only, because we know that, and focal length is also positive, 1 by f2, second equation. And from here we can write 1 by v minus 1 by u, so minus minus would become plus, please understand, is equal to 1 by f, right? And 1 by f is actually power of the combination. So look here carefully. If I add first and second, adding first and second, what we will get? 1 by v prime minus 1 by v prime is cancel out, and you get 1 by v plus 1 by u is equal to 1 by f1 plus 1 by f2. And 1 by v plus 1 by u is nothing but equal to 1 by f, which is equal to the power of the combination. So from here we get power of combination is equal to 1 by f1 plus 1 by f2, which is equal to f1 plus f2 into f1 into f2. This is the power of the combination. This question, you can expect this question in the category of 3 marks, because 1 mark is for the ray diagram and the 2 mark for the rest of the calculation. So this can be under the category of 3 marks. Okay guys, so I hope you all enjoyed the session. If you have any doubt, please comment in the comment box, and we'll see you guys in the next class. Take your time, note it down, and then we will see you in the next class. Okay, till then, take care, bye. Thank you so much.